All right, so let's continue with data types and operations. R basically allows you to do any operation that you could also do with an advanced calculator. You can add and subtract, you can multiply, you can divide, you can exponentiate, you can take the log, anything that a numerical software is expected to do is also possible in R. Very important are logical operators. Very often, let's say when we filter data or we want to build software that distinguishes certain cases, using if statements, for example, we're going to use logical operators. A logical operator in R is can be executed by, for example, using equality or inequality between variables. So for example, you can compare is 5 less or equal than 6. Since this is true, the resulting logical expression will be true. On the other hand, if the statement that we're testing is false, the logical expression will be false. Of course, you can also test equality. Is 5 equal to 6? Obviously, this is false. Most importantly, we can also store these logical values in variables or even vectors. This is going to come in very handy, especially if you want to filter data or select a subset, for example. And we're going to talk about this later. You can also combine logical operators using the AND or the OR operator. If you're combining two logical statements by using the OR operator, this basically means that this combination will be true if one of these two statements or both are true. So here we have, is 5 equal to 5? Obviously, this is true. Is 5 equal to 6? This is false. So here we have true and false, but since we use the OR operator, only one of them needs to be true, so the result is also true. However, if we use the AND operator, this means every statement that we combine using the AND operator needs to be true for the resulting statement to be true. So 5 is less than 6, true. 7 is less than 6, false. Hence, if we combine these two with the AND operator, the resulting expression will be false. Now, as I already showed you before in the first lecture, you can easily define objects in R by using this left-pointing arrow to define an object called X to be whatever expression you write on the right-hand side. So here we say that X is assigned the result of 2 plus 2. So X will be 4. In Stata, if you're redefining a variable, you have to say this explicitly. However, in R, this is can be done exactly the same. So you don't have to say that this variable X is already defined. You can just basically redefine a different new variable. So if we, for example, define Y to be 4, we can overwrite Y by saying Y is now Y itself squared. This also highlights an important distinction between assigning a value and testing for equality. So obviously, Y isn't equal to Y squared. But instead here, we're just saying that Y should be a new value, and that should be the squared value of the previous value of Y. So in this case here, Y is now 16. Stata has, R, excuse me, has 4 different data classes. We have numeric data that is either integer or floating point numbers. We have logical, that we just talked about. These are statements that are just true or false. We have character, which is strings of any length. Note that very often you have data that looks like a logical but it is in fact a character. So this happens quite often when you're reading data from a spreadsheet, that R doesn't immediately recognize that your value is a numeric value. So for example, if you accidentally read, if you have data that where instead of the decimal point, you're using a comma, and R doesn't understand that the comma stands for a decimal point. So it will just assume that this is a normal comma in a text and will read this value as a text value. And the resulting class of this, when you read this data, this will be stored as a character. So you cannot do any mathematical operations with it because multiplying characters is a pointless exercise, and therefore you first have to convert the characters into numerics. Last but not least, factor variables are to denote basically different groups. So they're kind of categorical variables that where the group itself doesn't have a meaning. For example, if you have industry code, this is something that you want to store as a factor because the industry code itself does not have the numeric value of the industry code is irrelevant. The only thing that matters is that different industry codes stand for different classes, stand for different industries, similar to sex or municipality. So if you want to know what the class of an object, there is a convenient function called class. So let's say we define A to be 2. We call class on the object A. It will tell us that this is a numeric. If we store B as 2, but we use quotation marks, this will be stored as a character. So generally, quotation marks tell R that this is supposed to be read as a string variable. If we assign C a logical value, this will be the class of this will be logical. And if we say true but with quotation marks, it will still be a character. So to highlight again that if you're reading in a variable that is actually supposed to be true, but something goes wrong, very often you end up with character values that look like logical or numeric values. Okay, so now let's talk about vectors and matrices. This is a very important chapter because whenever you're working with data, data is a matrix. So whenever you're reading a table or something, this usually comes in the form of a matrix, especially if it's numeric data. So the vectors in R are kind of as you would expect them to work from mathematics. They're 1 by n, the kind of objects that have dimension 1 by n. And to create one, you use the function c, and then you open brackets. And vectors can have, they can be character vectors or numeric vectors. So for example, if you want to have a vector that contains just the names of weekdays, you can say, we can call this object days, and you can assign it the vector that contains 5 different names of weekdays. Notice that all of these are written as strings, so this will be a vector filled with characters. On the other hand, we can, for example, have also numeric vectors. For example, for the temperature, we call this temps, and we assign it a vector that has the same number of entries, 5, 1 for each corresponding day, and each has a numeric value. We can also reassign the names of the entries in the vector. And this is done by calling the function names. Basically what names does is it takes whatever object that you have and it kind of opens up the names, and then we can do, for example, we can overwrite it, or if we want to read out the names separately, we can just call names of temps and we'll just display us the names. And in this case here, we have 5 numeric values, and we have 5 characters with the names of the days. And since they match in dimensions, we'll just assign each temperature value a weekday name. So something that is very important is the concept of using logical operators to subset temperatures, to subset vectors or data matrices in general. Here, for example, if you remember, we have these 5 values, and we just want to have all the days where the temperature was more or equal to 18. Obviously, Monday will not be selected. Wednesday won't be selected either. So we'll be left with 3 days: Tuesday, Thursday, and Friday. We can do this by basically using this logical expression inside the brackets of temperatures. And this bracket operator of the temps vector basically tells us which entries of the temps vector we are selecting. And I think at this point it's probably helpful to show you an example directly. So let's go to our studio. Let's continue where we left off. By the way, just to catch up with the previous video, the option quote in print works only for string variables. So let's say if we define y equal to 5, but in quotations. Now, if we print this, you see that it has quotation marks. Or if we say quote equals to false, there will be no quotation marks around it. So now let's create a vector. Call this vector vec to make it easier. Let's give it values 1, 2, 4, and 8. So if we're subsetting a vector, let's say we want to have all entries that where the value of the element is larger than 2. So what we're doing now, we say vec, then we open brackets, and now we say we want to have all values that are larger than, say, larger than 2. If I highlight this, we as a result get 4 and 8. What is happening inside here is that if we just call the expression inside the brackets, vec larger than 2, the result will be a logical vector. Because logical operations work for vectors in a element by element fashion. This means that what we're basically doing is we feed a vector of logical statements into the brackets inside here, and this tells R that we do not want the first element because it's false. We do not want the second element because it's also false. But element 3 and 4 are true, so therefore we want these 2 elements. Kind of to illustrate this, we can also say, for example, we can make a new vector called this select, and that's just vectors, let's say, larger than, all elements are larger than 1. Select is now false only for the first element, because all the other ones fulfill this criterion. And now if we use vec, square brackets, and we feed it in this vector of logical operations, of logical statements, it will give us the second, the third, and the fourth element and leave out the first one because here it's false. So this process of vectorization is very important whenever you're filtering data or trying to subset your data set. Let's go back to the slides. Okay. So what we can also do is, for vectors, we can apply vector algebra like we would do in mathematics. If we just, for example, look at an example here where we create a second temperature vector, we also assign it the same days, the same values for days. We can add these two temperature vectors together, and what this will do is it will add these vectors element by element. Afterwards, we divide it by 2, and if you're multiplying a vector or a matrix by a scalar in R, this works as you would expect from matrix algebra. It will just multiply each element in the matrix or in the vector by this value. So here each element will be divided by 2. So the resulting vector, the result of adding the two vectors together and dividing each element by 2 will be a vector of the average temperature over these 2 days. And we can see the output here. Now, matrices are two-dimensional matrices, two-dimensional vectors. And matrices, importantly, contain only one data type. So if you have more than one data type, if you want to have different rows that contain characters or characters, logicals, numerics, we want to have a data type, data frame. But if you just have matrices, they are usually a single data type, and usually they're numeric. To create a matrix, we use the matrix command. And the syntax of matrix is that we open the brackets. We input the first variable, which is a vector that contains all the data we want to fill into this matrix. Afterwards, we tell R how many rows and how many columns this matrix should have. And then we tell it by how it should fill this matrix, whether it should fill it by row. If it fills it by row, this means that it will first populate the first row with the data from the vector. Once the first row is full, it goes to the second row, fills this row, and so on, as opposed to by column, when it will first fill the first column, fill the second column, fill the third column. So let's look at an example. This expression here, 1 to 6, means it's a shortcut to write a vector that contains all variables from 1 to 6. So 1, 2, 3, 4, 5, 6. These 6 elements we then fill into a matrix with 2 rows and 3 columns, and we want to fill it by column because by row is false. So this means we start with the first column, take the first 2 elements, go to the second column, take the third and the fourth element, and to the last column, we take element 5 and 6. On the other hand, if we fill this by row, it will just take the first 3 elements, fill it into the row, and the second half of the vector, fill it into the second row. Important is also that you can populate matrices with data that does not does not have a corresponding dimensions. What R does, it first of all give you a warning, but it will still populate the matrix. It will just repeat the data from the beginning of the vector. So let's say we feed it in the vector that contains 1, 2, 3, and 4, but we still have 6 elements, so 2 rows and 3 columns. it will just fill by row 1, 2, 3, 4. Here it runs out of data. It will just go back to the beginning of the vector and fill the remaining entries. So whenever you're filling data, make sure you keep track of the dimensions, or just pay attention to warning messages, because R does not abort automatically. It will just often it will just execute the command and give you a warning, but if you don't pay attention or you explicitly suppress warnings, then you might not get you might not be working with the data you think you're working. Yes, obviously you can just create any vector and use this as an input as well. It doesn't have to be a vector that contains increasing by the same increments. It can be literally any data that you have. You can fill it into a vector matrix. And if you're only specifying the number of rows, the matrix will automatically have the dimensions that fits the total number of entries with that number of rows. You can also basically just combine different vectors. If you take two vectors and combine them together into a new vector, you will just create one extra long vector, as you can see inside here. And then you can fill this data into your matrix. So what you should mainly take away from this is that if you're programming, you can nest functions into each other. So what you're doing here is you're essentially nesting this C function inside the matrix function. So first, what happens is R will start with the deepest function. So you'll first execute this vector combination in here, and afterwards it will apply the result of this vector combination to the matrix function. You can do this as many levels as you want. However, it is generally advised that you don't do this. You don't nest functions too deeply, but rather just save these variables as separate variables, or save these commands, the output of these commands as separate variables, and then use them as an input. It just makes your code much more readable. Since when we're looking at matrices, we have two dimensions with rows and columns, that means also we need names for rows and columns. So instead of just a names function, we use the function row names, which works the same way as with names. The only thing is it explicitly only gives you names for the rows. Call names, it does the equivalent for columns. So for example, in the temperature matrix, which is just a combination of these two vectors that we had before, we created here, if you remember, it had 2 rows and 5 columns. So since you have 2 rows, it will basically, each row will be a week. So we will, if we rename it, we need to rename it with, we need to have 2 values. And we call this week 1 and week 2. And the columns are still the weekdays, so we can reuse the days vector that we've used before. And the result will be this small vector that has weekdays in the columns and week 1 and week 2 in the as row names. Also very useful is that you can do matrix algebra in R. However, you have to pay attention that if you're multiplying using the conventional multiplication symbol, R will not interpret this as the matrix multiplication. However, it will multiply element-wise. So if you, let's say you have this vector A, which has the entry 1 and 2, and then you have this matrix B, then if you are just multiply it like that, what you will do is you will just multiply the first element of the first column by the first element of the vector, and the second element of the first column by the second element of the vector. And then you will repeat this. You will multiply the first element of this column by the first element of the vector, and here with the second. If you know anything about linear algebra, multiplying a vector of dimension, or a vector of length 2, and the matrix that is 2 by 2 will result in a vector of length 2 as well. It will not result in a 2 by 2 matrix. And you can see this here. If you use mathematical matrix multiplication, you use the multiplication symbol inside 2% signs. So then you would multiply vector A with this multiplication in percentage signs matrix B, and this will actually give you the matrix multiplication that you know from linear algebra. You can also have access to all other functions from matrix algebra. For example, the inverse. The inverse in R is can be called by calling the function solve, because usually when we use the inverse, we use it to solve a system of equations. And then if you multiply matrix B by the inverse of matrix B, this should result in the identity matrix. And in fact, if you look at it, on the first glimpse, you think probably that this is not the identity matrix. However, if you look at it, if you have 1 on the diagonal, you have 0 here, and here you don't have 0, but you have an extremely small number. And basically what this is R is not solving the inverse of the matrix B mathematically, but rather numerically, which means that it just approximates it, because taking the inverse of a matrix is a very computationally intensive operation. And therefore it will take, especially if you have, for example, taken the inverse of a very large matrix, if you're doing OLS, for example, it will take much too long. So what R does instead, it takes a numerical approximation that is very accurate, but it is not exactly precise. So as a result, you will just have a value here that is so small that it's basically indistinguishable from 0, but it's not exactly 0. And this is just something that you should be generally aware of, that whenever you're doing something that involves very small or very large numbers in any programming language, basically, you might run into trouble of lack of precision, because your computer is only able to handle a certain level of precision. And as soon as you go below that, the computer will just basically round the number down or something. This can, for example, happen if you do something like doing maximum likelihood, for example, where you're basically multiplying a lot of values that are between 1 and 0. And the product of this will give you a very small number. And therefore, it's likely that at some point, the number is so small that the computer runs out of precision, and it basically just rounds it down to 0, even though mathematically it will never be exactly 0. This is just something to keep in mind when you're writing your own functions. So there are obvious ways around this, like, for example, taking the log likelihood when you're doing maximum likelihood. But it's just a word of caution whenever you're writing your own numerical routines.